continuing our theme of thinking about which individuals are actually in the population, and that individuals vary based on their contribution to population growth because of differences in things like age or sex or reproductive class, we're going to use population projection matrices to follow populations through time. Now, this is not as bad as it sounds. It's actually just kind of a way to simplify our understanding of what's going to happen to a population in the future. Let's start out by building our matrix. If you haven't done matrix algebra before, it's okay. It's pretty straightforward. We're going to walk through it. It's just a kind of a simplified way to keep track of who's doing what. So, to build this matrix, we're going to start here with a group of 3 age classes. For our current example, we're going to imagine that there are 3 age classes. So pre-juvenile, juvenile, and adult. You could imagine pre-juvenile maybe being something like egg, juvenile being a larval form, and then an adult being the adult. All right, and then I have pre-juvenile written up here. So what we're going to have here is a group of 3 numbers that are going to tell us if we're talking about a current pre-juvenile, the chances of being a pre-juvenile, a juvenile, or an adult during the next time period. So in other words, if they're currently an egg, for example, what are the chances of still being an egg next time, or turning into a juvenile, that is, say, a larval form, or turning into an adult? All right, so we're always going to read this from the top one to the one on the side. For our hypothetical example here, let's imagine that these are the numbers. So in other words, if an egg is currently an egg, it can't stay an egg for next time. It either has to become a larval form or it's going to die. All right, so 0 chance for an egg to remain an egg. A small chance for the egg to become a larval form. So, and according to this, most eggs aren't going to make it. And the egg can't jump directly from being an egg to being an adult, so we have another 0 there. All right, so everybody see where those come from, hopefully? Our next column in our matrix, we're going to be following the juvenile form. So perhaps the juvenile could reproduce, so that'll put a number here. The juvenile could remain a juvenile, or the juvenile could become an adult. So let's have these numbers. So according to this, a juvenile could reproduce when we have on average 52 eggs produced. Juvenile could remain a juvenile, so there's a 25% chance that a juvenile remains a juvenile, or a juvenile could go through metamorphosis and become an adult. 8% chance of going through metamorphosis and becoming an adult. All right, so based on this, I'm going to ask you a question. What are the chances that a juvenile dies before the next time period? The answer is going to be 67%. Because the juvenile has a 25% chance of staying a juvenile, has an 8% chance of becoming an adult, so that's a 33% chance of still being alive. That means there's a 67% chance of dying. All right, hope that makes sense. So juveniles on average produce 52 eggs and have a 33% chance of staying alive. 25% chance of that is remaining a juvenile. 8% chance of that is turning into an adult. And then the other 67% is that they don't survive. Okay, our last column here in our matrix. So this is figuring out what's happening with the adults. So once again, this first row is going to be that reproduction. And then we're going to ask whether the adult could go backwards to become a juvenile again. And then the chance of an adult surviving to remain an adult next year. In other words, to still be alive. So let's imagine that the adult produces on average 279.5 eggs. That adults can't go backwards in time to become a juvenile, so we got a 0 there. And then there's a 43% chance that the adult will survive to still be an adult next time. All right, so we're going to call this a vital rate matrix, and it's just going to be a way to keep track of what's going on with our different age classes. So average reproduction, and then average chances of turning into these various age classes or remaining in the age class they're already in. Okay, the next thing we're going to add then is this little skinny matrix that we're going to call a vector. Just a single column of numbers here, and these numbers refer to the number of individuals currently in those age classes. So for our example, we have 70 eggs, 20 larvae, and 10 adults in our current population. So we can imagine that that was our current population, and then these vital rates will tell us what's going to happen to the individuals from our current population. When we have things set up like this, it makes it really easy for us then to figure out what the next year's population is going to be like. So what we're going to do is we're just going to multiply our vital rate matrix, so on the left here, by our little skinny matrix, our vector here on the right. Now, again, if you haven't done matrix algebra, don't worry. It's really straightforward. All we're going to do if we multiply these is that we're basically going to turn our vector sideways and multiply each of these numbers by the respective number in the vital rate matrix. So if we do that, we take the 70, multiply it by the first column, the 20 multiplied by the second column, the 10 multiplied by the third column. That is going to tell us how many eggs are going to be produced. So the eggs don't produce any eggs, so 70 times 0 is 0. There are 20 juveniles. They on average produce 52 eggs. And then there are 10 adults, and they on average produce 279.5. We do the math, and we end up with 3,835 eggs. The next step then is to do that same calculation, but just move down a row. So everything is exactly the same. We're just one row lower. So 70 times 0.024, 20 times 0.25, 10 times 0. We do that math, 6.68. And then finally we do the same thing. Take our 3 columns and multiply by the adult row. What do we get? 5.9. Now, we should maybe do some rounding here because you can't have like 9/10 of an adult. So we could round that to 6 adults, 7 juveniles, and then we still have our 3,835 eggs. And so what do we get? We get our new vector, our understanding now of what the population is going to be like next time. Right? And then we could take that one and multiply by that vital rate matrix and figure out what the population should be like the next time. Right? It's just a quick way to keep track of what's going on, of how those vital rates are affecting the population, what that population is going to be like. Notice that in our first time step here, our population has really changed. It's gotten much larger, but the vast majority of that is now eggs, and actually the number of juveniles and adults has decreased. If we follow this population through time, we'd be able to see how those proportions change from year to year to year. Now, something that I guess you could probably probably just makes sense is that these vital rates here, these are often going to be things like averages. And so we know that it's not necessarily going to be those exact values every time. So it's possible to add variability into your vital rate matrix. Right? So we can look at that same matrix, but instead of having a number here, we have an X. And down here in the bottom right, we have a Y. What those are would be then a distribution, right? That we know that the average number might be 52, but that there's variability. And so if we have enough information from our population, we could say, well, we're going to multiply out our matrices here, but we're not going to have 52 there every time. We know sometimes it's going to be 51, sometimes it's going to be 53, sometimes it's going to be 50, right? And so that's a variable. Not a variable that you'd solve for, but just a variable that would represent that variability in what that value is going to be from year to year. And so if you're doing these calculations and want to know how your population is changing, well, you could multiply by a different number there every time if you had enough information to know what that distribution would be like. Everything would be the same, it's just that X and the Y would change values every time. Now, if we think about a population that we're following with a population projection matrix, at some point, we're going to have a stable age distribution. So, in other words, if things stay relatively consistent over time, then at some point we're going to reach a situation where the proportion in each stage is going to be constant, right? We're going to reach the point where we're going to say, like, I don't know, like 85% of the individuals are eggs, 10% are juveniles, and 5% are adults, or whatever it might be. That stable age distribution is going to take a little while to reach. We saw in our previous matrix when we were multiplying things out that the numbers were really changed quite dramatically that first generation. But eventually a population will get there. That stable age distribution is not going to be affected by the initial numbers of individuals. Additionally, the way the population is growing when it reaches that stable age distribution is not affected by those initial numbers. What can be affected, though, is how long it takes a population to get to that stable age distribution. Right? How long, you can see it in the graph here, where it's kind of bouncing around at first before it hits that stable age distribution. How long does it take to get there? Well, it depends on a couple of things. One, it depends on how many individuals are there at the beginning, and so if the population is already really close to stable age distribution, then it's not going to probably take as long to get there. It's also the specific vital rates that we put in the matrix. Those are going to affect how long it takes to get that stable age distribution. We can kind of make a generalization that for most vertebrates, it'll probably take around 20 generations of that kind of bouncing around here before it reaches that stable age distribution. And then, assuming conditions remain relatively consistent, it'll stay there as long as everything stays about the same. All right, so again, why are we doing this math? Why do we care? Why are we thinking about this? This gives us a way to estimate what's going to happen in our population, how the population is going to change, how the proportion of individuals in each group is going to change, what we expect to see for the population over time. And so if we're in charge of managing a population that we want to get bigger, we could do those calculations, follow that population out for multiple generations, and figure out what we expect to happen with it based on those vital rates that we put into that matrix. We're going to think about how populations are going to react to those different effects of those different vital rates. That all the vital rates have different consequences for their influences on the way populations grow. And often, those effects are not very intuitive. Let me give you an example. What we have here are some pictures of some sea turtles. And we're going to divide the sea turtle life into, let's imagine, 3 stages. On the far left are the hatchling sea turtles making their way down to the ocean. In the middle are juvenile sea turtles out in the ocean. And then on the far right are the adult sea turtles, who basically reach their large size. Now, we as humans, we like sea turtles, and a lot of sea turtles are endangered. And so we're interested in how we might be able to help the sea turtles. What could be done to increase the population size of sea turtles? Well, when sea turtles are hatching, we can see them on the beach. They're hatching out of their eggs, and they're trying to make their way down the beach into the ocean. When that's happening, it's a pretty dangerous time for those baby sea turtles. Lots of things eat them. Here's a picture of a black vulture eating them, raccoons eat them, weasels would eat them, anything that happens to be around, possums would eat them, hawks would eat them. Anything that happens to be around when those baby sea turtles are trying to make their way down the beach, well, they're probably going to try to eat baby sea turtles. And so we as humans have seen this and said, oh no, poor little baby sea turtles. We need to try to help them. This is a way that we could help sea turtles, is if we have people out there and have protection, maybe some fences and things to keep other things out of there, we could prevent the vultures from eating the baby sea turtles. And so more sea turtles make it into the ocean, more sea turtles make it into the ocean means more sea turtles overall. Right? And so we've put a lot of time and effort into protecting baby sea turtles on their way to the ocean. Not that there's anything wrong with that, but it turns out that that's not really what affects how well the population is doing. That in reality, the population growth is most sensitive to the survival of adult sea turtles. That's the thing that really determines how big the population is going to be. And so the efforts that we put in order to help baby sea turtles make it down from the hatching into the ocean might make us feel good, but it's not really having much impact on the size of the population. That it's really all about keeping those adult turtles alive is what's really going to matter. And so when we're dealing with trying to manage populations, we're always dealing with limited time, limited money, limited resources, limited everything. And so you have to figure out where that time, money, and resources will be most effective. And a sensitivity analysis helps us to see where our efforts will be most effective, what will do the most and what probably won't have much effect on the population. Now, the easiest way to do a sensitivity analysis is just go in to that vital rate matrix and start, messing around with it, right? See if I increase this number a little bit, what effect will that have? Or if I decrease this number a little bit, what effect does that have? Which of these vital rates has the biggest consequence for our future populations? Right? By doing that, then we could see, well, if I change this number, wow, that's really going to matter. Or if I change this other number, not so important. We can actually make some generalizations. If we don't have enough specific information for a population to do a vital rate matrix and to do all those calculations, we can make some generalizations. For populations that start reproducing pretty early in life and have a lot of offspring, that is to say, species with a relatively fast life history, generally reproduction is the most important aspect controlling how well the population is doing. On the other hand, for a species with a slow life history, well, it's really the adult survival that is going to have the biggest effect on the size of the population. Right? So these are some generalizations, not necessarily going to be true in every single case, but if we don't have better information, this is what we would expect to find with different species life history types. We're going to look at some actual examples of some real-life species where these sorts of decisions had to be made to figure out how best to deal with those species. So we're going to start out with an endangered species, the red-cockaded woodpecker. Red-cockaded woodpeckers are found down in the southeast United States. Like most woodpeckers, they nest in cavities, so they nest in holes in trees. You can see in the picture there. Red-cockaded woodpeckers, because they are endangered, we have this concern about trying to manage them to maximize the size of the population. And so we ask the question, well, how do we maximize the success of red-cockaded woodpeckers? And people who were working with them came up with 4 different options for how they thought might best improve the size of the population to help the red-cockaded woodpeckers. One option was to get rid of invasive species. So, for example, other birds like starlings would compete with red-cockaded woodpeckers for holes in trees. So one suggestion was, let's get rid of the starlings, therefore the red-cockaded woodpeckers won't have as much competition for nesting areas. Another suggestion was to move females to other areas, right? To take areas that had a surplus of females and move them to other areas that maybe didn't have as many females. Females, being the ones that lay the eggs, were the ones that are going to determine how many offspring are produced. And so by moving those females around, perhaps they could be maximize the reproductive potential of the species. Another possibility, create cavities. So maybe they're limited, maybe they don't have as many places, as many holes in trees to nest in, so they can make new cavities, and they could do that either in areas where there were already red-cockaded woodpeckers or in areas where there are not red-cockaded woodpeckers, in hopes that it would increase the number of successful nesting attempts. Right? So, sensitivity analysis would say, not all of these are going to be equally successful. Not all of these should be implemented, perhaps. Maybe we need to figure out which ones will be most effective at helping the population. One of the first things they found, that female translocation, moving females around, not successful. Not really helping the population, not doing much to increase population size. What they did find was the other three strategies were all potentially helpful, but the one that really mattered was making large cavities or making new cavities in areas where they were not currently found. So if they did that, then red-cockaded woodpeckers would start living in those areas and would be more successfully reproducing. Right? That was what the population growth was most sensitive to, was having cavities available in areas where they weren't currently living but could potentially move to. All right, well, that's an example of an endangered species where we're trying to increase the population size. Let's look at another example, and this is an example of a species that's a pest. In other words, a species we want to decrease the population size. And our example here is a bird called the brown-headed cowbird. Brown-headed cowbirds are a native species throughout the eastern United States, but their population has greatly increased because of the actions of people. We have, by fragmenting the habitat so much, we've created lots of areas that brown-headed cowbirds really like. Brown-headed cowbirds prefer the edges of forests, and we've created lots and lots and lots and lots and lots of edges. And so brown-headed cowbirds have started doing really well. All over the place. Much higher population than they used to have. The concern is that a brown-headed cowbird is a brood parasite. In other words, brown-headed cowbirds don't build their own nest, but instead the female will lay her eggs in the nests of other birds. Sometimes when she does this, she'll kick out the eggs of the other bird. Sometimes after the offspring hatch, they'll push the eggs out or will kill the other nestlings. And so the outcome is that if a nest has a cowbird egg in it and that cowbird egg successfully hatches, that the only thing that we raise in that nest will be a baby cowbird. And so you end up with a situation where you have, for example, this yellow warbler is feeding this cowbird, which is much larger than the yellow warbler. This yellow warbler is not going to be having any offspring of its own this year because it's devoting all of its time and energy to raising a baby cowbird. Now, that's a concern for our native species because we have created so many additional fragmented habitats that the cowbirds really like that our native species end up being much more susceptible to brood parasitism than they would have been historically. And especially some species like Kirtland's warblers, which are endangered. So, we look at the brown-headed cowbirds, and especially around places like where the Kirtland's warblers breed in Michigan, and say, okay, what do we do about this? There are so many brown-headed cowbirds that Kirtland warblers are not being very successful because the Kirtland's warblers are raising baby cowbirds instead of baby warblers. So, management options. 1, find and remove cowbird eggs. Right? Look around, look in the nests of the Kirtland's warblers, for example. If you see an egg that looks a little different, it's probably a cowbird egg, get rid of it. 2, remove adults in the winter, or 3, remove adults in the summer. Now, let me make it clear here. When I say remove, I mean kill. Right? So, in the winter, cowbirds tend to get into big flocks, so it might be easier to kill a bunch of them. However, in the summer, if you kill them, you'll probably kill the ones that are actually closest to the Kirtland's warblers. Some of those ones that were around in the winter, well, they probably didn't make it just because the winter time is a tough time. Some of them went other places, so maybe they weren't a threat to the Kirtland's warblers. If you wait till summer, maybe you can target the ones that are most likely to be a problem for the Kirtland's warblers. All right, so a study was done looking at different aspects of life history and the effect that those different aspects of life history had on the population growth rate of brown-headed cowbirds. All right, so let's start looking around here. The way that this is set up is the y-axis in all these graphs is the population growth rate. All right, so how much the population is changing. And in this case, they were using lambda because this is a seasonal life history species. And so the x-axis then are these different aspects of life history. And we can see how important those different aspects of life history were in affecting that population growth rate. So, for example, if we look at adult survival, this middle one on the right here, we see that the R-squared value, if we look for a correlation between adult survival and the population growth rate, the R-squared value is only 0.07. In other words, the survival of the adults explains about 7% of the variability in the population growth rate. In other words, not doing much. Yearling survival, adult survival, yearling fecundity, adult fecundity, so nestling survival, all of these things are not explaining much of the variation in population growth rate. In fact, the only one that explains a significant amount of variation in population growth rate is the egg survival. If the eggs survive or not has a big effect on how that population is going to do. The rest of these things, matters a little bit maybe, but not too much. So, based on that, we would say that the population would be most sensitive to egg survival, and so that would be the best management option. That getting rid of the adults doesn't really have much consequence for this brown-headed cowbird population, and therefore for things like Kirtland's warblers. However, there's this issue. And the issue is that finding and removing cowbird eggs is a pretty time-consuming and invasive process, right? Because you have to go out there, you have to search and search and search for the nests, and then once you find the nest, you have to reach in there and look at the eggs and figure out which egg to get rid of. And sometimes when that happens, that increased amount of disturbance causes the native species to abandon their nests. And so, while removing the eggs would have a big consequence for the brown-headed cowbird population, it may not be practical, it may not be something you can actually do because of the negative consequences for the host. And so, we may not be real great at controlling cowbirds based on this study. All right, third option. We're looking at a game species. In fact, multiple game species, specifically waterfowl. So, waterfowl tend to breed in the northern part of the continent, North America, and are hunted in the winter range. So they breed up, in the maybe the tundra, and then they come down here and are hunted in the winter. Historically, organizations like, for example, Ducks Unlimited, have been really interested in maximizing the size of waterfowl populations because they want to have waterfowl to hunt. Right? And so they have spent a lot of time and energy and effort trying to maximize the number of individuals in these populations. And there are really two main ways that people have looked at helping waterfowl populations. Helping so they have them to hunt, but still helping. One is enhance the breeding range, right? So the breeding areas, increasing the quality of that habitat. And the other is the wintering range. Now, historically, most of the money was spent on the wintering range. That less than 40% of funding available was spent on the breeding range. However, when they did a study, they found that the breeding range is actually by far the most important determinant of the population of these waterfowl. That what happens there really, really matters. In fact, the study showed that 84% in the variation of lambda came from the breeding range. Right? It's almost all about the breeding range, how the population is doing, even though historically we've spent a lot more time, energy, effort, and money on the wintering range. That the variation in lambda, only 9% comes from the wintering range. That it's not about where the ducks are wintering, it's about where the ducks are breeding up in the north. And so if we really want to maximize the size of these waterfowl populations, to do so, you need to spend more time, effort, and funding on the breeding range. That is the part of the life cycle that is most sensitive to intervention.